What do you think is the difference? Right, so on one side we have probability, and then we have statistics. Yeah. I mean, they're certainly related. So what do you think is the difference? Anyone?
Probability is generally a tool for handling uncertainty, whereas statistics are used to understand patterns and things like distributions.
When you say distributions, that's also probability, right? So, I mean, certainly, both deal with distributions, both deal with uncertainty. And we talk about probability when we are doing statistical analysis. But what is the key difference? When we say statistical analysis, is it just probability or is it something more?
For statistics, you have data and you want to make an inference.
Exactly, right? So the clue was already when I said statistical inference. So when you're making that inference from data, it means some parameters are unknown. Whereas probability is what you evaluate. You already know the distribution, or you're specified what it is, and then you can evaluate the probability. So in that sense, we employ probability in the statistical analysis, but statistics deals with unknown parameters, right? It deals with making inferences, and that's the key additional component when we think about statistics, right? So as I said, the key aspect is inference. And when we say inference, we mean we are trying to infer something that's unknown, right? The data tells us what's otherwise unknown. And within this, there are two main kinds of inference. One is detection, and the other is estimation. And detection is really a special case of estimation because, generally you have a parameter you want to estimate. Detection is the special case when that parameter is discrete, so there's only a discrete set of choices for that parameter. So that's the subdivision we do when we think about problems, because detection in many cases ends up being simpler than estimation. And so what are the ingredients for doing statistical inference? We said we have to have data, right? So let's say we have some variable y. This is the observed data. I mean, could be a scalar, vector, matrix, all kinds of data, right? So for now, we'll mostly deal with scalars in this class, as a starting point, but we can always extend it to more complicated cases. Yeah, so we have observed data, and we then want to make an inference. So we want to make an inference about some unknown parameters, and we'll represent those unknown parameters as theta. Right, so the data can inform us about the parameters of interest, and we'll represent that through theta. Right, if the data can tell us something about the unknown parameter theta, it means they have to be related. So how do we model that relationship between the data and the parameter? How do we connect the two?
You have a likelihood of what's in the parameters from the data and vice versa.
So you want to kind of ask how the probability of y is related to the parameter theta. right? And likelihood is related to probability, but we'll come to likelihood in a minute because we haven't formally defined it yet. But that's the idea, right? So you have theta here, you have y, right? So what is the thing in between that connects the two? That's the model, right? And the model is nothing but gives you the probability of seeing these realizations of our data under this parameter theta. So we'll represent that distribution through f. Right, so this is the basic setup for talking about statistical inference, right? We need the data, we need the unknown parameters, and the two are related through the model. Right? And so now the question is, what can we further say? Like, we can ask, okay, what do we know about the model? What do we know about theta? What is the distribution, family of distributions we can put in the model, right? So we can provide more details to set up the problem. And that's where we'll have more choices for modeling. So there are mainly two philosophies. I guess you may have come across this. It is frequentist versus Bayesian. So can someone describe to me what's the difference between the two? We have this basic setup here, right? So what would be the frequentist assumption or notion versus Bayesian notion?
So frequentist says the unknown parameter is actually a real value. It's not a random variable. It's an unknown parameter, but we don't model it as a random variable. But the Bayesian case is like they also model the unknown parameter as a random variable, so they put an uncertainty quantification in this unknown parameter.
Right. So I guess the main term is deterministic, right? So theta is deterministic and fixed under the frequentist assumption. Whereas in the Bayesian, theta, is a random variable. But what's the main philosophical difference here? When we say theta is a random variable, that means we are assigning a belief to it, right? So the idea is in the Bayesian world, probability is subjective. It depends on what prior belief you have, and then you can reason about the posterior based on the prior belief. On the other hand, in the frequentist setup, theta is fixed and deterministic, so that means the probability of the outcome is objective. It's something fixed but unknown. And of course, you can ask, what's the right notion? And this is more than a century-old debate, right? So which means there isn't just one right notion, depending on the framework and depending on the computation available, you can decide which one to pursue, right? So both have their strengths and weaknesses. So what would you say are strengths of the Bayesian setup? What's good about doing a Bayesian formulation?
As you mentioned, it does lend itself to uncertainty quantification if you have a distribution for your parameter.
Right, so I guess, I'll be careful using the term uncertainty quantification because we could do that for either, right? Because uncertainty of what, right? So, whatever are parameters of interest, we can try to reason what are the error bars, what kind of errors we are making. But that's different from having a prior belief, right? So I would differentiate the two. So let's kind of, call this the prior and not just the uncertainty, right? So it's a special a form of information available on this underlying parameter. And it may not be informative, that's another special case, but the main idea is that this has priors. So if you actually had useful information about theta, then you can incorporate that into your modeling. Whereas the frequentist setup does not allow that, right? So there's not a clean framework to directly incorporate that. So that's the main strength, that you can incorporate prior information into the modeling. What's the downside of Bayesian formulation? Yeah.
It's typically intractable.
Right. I mean, very super expensive, right? So, the computation could be exponential. It is exponential in most cases in the dimension. So if computation was not a barrier, probably we would all argue for the Bayesian formulation. But the challenge is many times we are limited, and the frequentist one, can be much more tractable, so that's the main, I would say here. This is typically less computation. I mean, not all the time, but typically, right? This is. So the main, again, but also what we compute is also different in the two cases, right? So in the Bayesian one, that's because we are doing the full posterior distribution. Whereas here, we are estimating whatever is our goal, right? Like if theta is the parameter we want to estimate, we are coming up with an estimate of theta. So that's the main, aspect, that when you talk about Bayesian computation, you want to compute the posterior distribution. And so we'll define what this posterior is, right? So to set this up for Bayesian, we have the prior distribution. So that's typically, we'll use this notation pi of theta throughout this course. So you have the prior distribution, now you have the model. So what is the model now? So earlier I had just described the model as distribution of the data y as a function of theta. But in the Bayesian setup, there's one additional detail. How can I model the relationship between the data and the parameter under the Bayesian formulation?
Use Bayes rule?
Right, so but before Bayes rule, yes, naturally we'll use the Bayes rule, right? But that's the next step. So one step before that, so what should I write down for the model? And then I can apply the Bayes rule.
The data given the parameter?
Exactly, so that's the conditional distribution, right? So here you have this, earlier we were just writing the distribution of the data as a function of the parameter theta, but now in the Bayesian formulation, it's the conditional distribution. Because theta itself is random, I have to write this as the conditional distribution. So that's the main difference. In the frequentist, right, this model is a function of theta, but theta is fixed, right? So this is the frequentist setup. But in the Bayesian world, this is the conditional distribution. So now how do I use the Bayes rule, or what do I, how do I make the inference in the Bayesian setup?
The f parameter given y equals the prior times the model with some normalization.
So first of all, what should I compute?
The posterior.
Right. So what is the definition?
It would be f theta given y, or
Exactly, right? So it's the probability of what is the theta given I have this data, right? So given that the data, the random variable y took the realization little y, what is my distribution of theta? And here I can use the Bayes rule, right? So I can write this down in terms of the just the probability of y, and then you have the joint probability, of course, of theta and y. And this you can further expand it in terms of the conditional probability and the prior. Can you see in the back? So it's nothing but you have the conditional distribution, which is nothing but the model times the prior, and then there's the normalization, right, with the probability of y. Right? Is this clear? So we'll compute the posterior, which is now the probability distribution of theta given the data. And we can use Bayes rule there. And what the Bayes rule allows us to do is to use the model and the prior, right, to get the joint distribution. Whereas in the frequentist setup, we don't have the posterior. All we have is an estimate we can give of the unknown parameter theta. We'll usually call it theta hat, and that's a function of the data we have. Right? So this is the estimate. So it's a function. It's a deterministic or a random function, right? So it could be both. So any questions between the two frameworks? Right? We have the frequentist framework where the unknown parameter is fixed, and then your goal is to find an estimate of that parameter given the observed data. Whereas in the Bayesian one, the unknown parameter has a prior distribution, and then you compute the posterior, which is the conditional probability of this unknown parameter given the observed data. Yes, so that's the goal. So the goals are different in the two frameworks. Right? And so so this was, right, the two ways we can solve the problem. And as I said, the two types of inference we typically think about are detection and estimation. Right? So the detection is when theta is discrete, whereas estimation is when the theta is continuous. And in so many cases, detection turns out to be, in general, detection is easier than estimation. So that's why we'll first study detection, and then we'll move to estimation. And detection is also many times called hypothesis testing. And this is in fact the foundation of scientific method, right? Because what the scientific method asks for is formulating hypothesis, then you go do experiments, and either you accept or reject the hypothesis you have, right? So that's the And so you can, relate that to the statistical analysis as well. And so what the hypothesis test means is, right, there are as many hypotheses as the number of realizations of theta, right? So let's say in the detection setup, I have like theta taking just 2 values. In the special case, we call it the binary hypothesis testing, right? So we are just testing for one or the other hypothesis, and there's also special names for the 2 hypotheses. One is the null, the other is the alternate hypothesis. So again, these are terminologies, but these are standard in statistical literature. So what this typically means is null is like the normal condition, and alternative usually something anomalous or something you're really looking for. For example, you can have like an operating plant, and the null hypothesis is everything's operating normally, and the alternative is when there is an anomaly. So typically, if you can distinguish the 2 in the sense of the null is the one which is standard operating or normal setup, whereas the alternative is where there is something unusual happening, you can distinguish it through these names. So that's the setup here. And then when we say hypothesis testing, we mean that we are testing whether theta is either theta 0 or theta 1, right? So we are like going and testing what realization or what is the value of theta. And that's why we also call this as hypothesis test. Good, so that's some setting up some terminologies when it comes to detection and estimation. And just one more before we proceed forward is parametric versus non-parametric. So can someone tell me what is the difference between the 2? What's a parametric distribution?
So you can have a distribution that is kind of like theoretical, that's generated, like has a CDF based on some parameters as a function. Whereas non-parametric, you can have some empirical data that you have a CDF for, but it's not really clear like what base distribution it came from.
Right. So parametric really means, from the name itself, right? There are parameters that describe the distribution based on some family. So you have some family of functions, and then based on how you select the parameters, you get the distribution. And so that's the, for example, if you think about normal distribution, right, Bernoulli, exponential, all these are parametric distributions, right? Because you can write down the distribution function, and then you can specify these are the parameters that, give rise to the function. Whereas non-parametric is when you cannot do that. You can't write it down as a family of functions. And in this part of the course, we'll be dealing with only the parametric part, right? Because indeed, we are thinking of the parametric formulation here. We are saying that the distribution is parameterized by these unknown parameters, theta. So we'll be limiting to that framework, but of course we have to start here before we can get to more complicated cases. So, if you're using neural network or kernels or all these other formulations, those are non-parametric, right? There you're not having a fixed family of distributions, but this is something you're also learning from data. So that's more complicated, but we would need it when the data is complex, like images, speech, language. All that cannot be dealt with just parametric family, right? So we would need to ultimately deal with it, but in the beginning we'll be dealing with parametric class of distributions. So that's another, just again, terminology. Any questions so far?
So how does non-parametric framework fit into Bayesian setting. So because we need the privately parameters in Bayesian setting, how does these two go together?
Right, so you can have Bayesian inference in a non-parametric setup, right? So the question is, how are you, what is the model here? So is the model like a fixed family and you can specify how theta gives rise to y, or is it not, you cannot write it as a fixed parametric family? Right, so I mean this overall setup is still the same, right? The main difference is here in the model. Is it parametric or non-parametric? Does it make sense? Yeah, it's at the modeling level. For instance, if in this setup, if theta, let's say, is the what's in the image and y is the image, right? You can't use a simple parametric model like Gaussian or Bernoulli or any of those distributions. And then we can think of non-parametric formulations. Right, so when we talk about the distribution, it's with respect to the model. Yeah. Good. Any other questions? So yeah, so the next part, right, so far we set this up. So I think, earlier we said likelihood. So let's now formally define likelihood. So far we've talked about the data, model, and the unknown parameter, right? So what is likelihood? Yes, I'm sure, when I say likelihood of something happening, it usually means probability of the outcome, right? But so is it exactly the probability, or is there a difference between likelihood and the model distribution? I mean, it's nearly the same. The main difference is it's up to a normalization term. So we'll use L for likelihood. And I'll just use this notation. If it's Bayesian, you have the conditioning, but we can kind of stick to this unless we specify it's the Bayesian setup. So the likelihood is related to the model distribution, but the only additional part is there could be a normalization term. And the main important part here is that this doesn't depend on theta, right? So you can ignore factors in the distribution that have nothing to do with theta. And why is that okay?
You often want to optimize with respect to theta?
I mean, it doesn't inform you about theta, right? It's not giving you any information about theta. So if you don't have this gamma of y, it doesn't affect your ability to estimate theta. And so that's why sometimes it may be just convenient, there's some complicated term here I don't have to deal with. And so that's the main difference, so likelihood and probability, when colloquial terms we use them interchangeably, but when it comes to definition, there could be a difference in the normalization. And many times we'll also use log likelihood, which is just the logarithm. Again, it's for some distributions, we'll look at the exponential family distribution there. Taking the log is the natural thing. So that's the. So I'll be using capital L for log likelihood. Right, so that's the definition. So now we can let's look at a problem, and then we'll further ask, how do we go about setting up the detection and estimation problems. So I guess the most natural problem to think about Let's look at normally distributed data. I'm sure all of you have done various problems using Gaussian distribution. So let's say I have IID samples from normal distribution. And let's say I have unknown mean here. So there is mu, and then there is some unknown variance as well. So here my set of unknown parameters is both the mean and the variance. Right? And my data, I'll put this as a vector, is, let's say, my NIAD samples. So it's normal distribution, I can write down the normal distribution. Right, and because it's IID, it would be just a simple product of the marginal distributions. So I guess I'm just looking at the, what is it, 2 pi sigma square to the n. And then I have the exponential term, right? Right, so all I've done is just write down the PDF of the normal distribution. Now I can write down the likelihood. So, I mean, again, I could write down the likelihood. I can, I don't have to write it in length, but I can also write down the log likelihood where, I would have this term and then some, right, like log terms that, you have only the sigma square. So one thing I want you to see here, right, so let me, make this clear. So when I write down the distribution here, I can ask what is the dependence on all the observed data? Is there a one-to-one mapping from this vector y to this probability distribution? Is it one-to-one? Meaning each vector here has a mapping that is, right, like unique to this function here. Or is there some reduced form that's, fix that, it would be the same value of the distribution? So I can expand this further, right? So I have sum of I. So there's one term with yi square, and then there is another term with yi, right? I mean, I can. So the dependence on the vector y is only through these two terms. Do you see that? So do I really need to know the value of each yi, or is it enough for me just to know this? What do you think? So if my goal is to estimate the unknown mean and unknown variance, what statistic should I be using? What is enough or sufficient for my estimation problem?
You only really need to know the variance of the data.
What does variance of data mean?
Like the you'll need the sum of yi squared and sum of yi.
So you would need to know only these two,
Yeah.
right? Do all of you see that? Right, because if I expand in my distribution function, the dependence on the data is only through the sum of yi square, right, which is like the empirical correlation, and then the mean, empirical mean, right? If I normalize, it becomes the empirical mean and covariance. So what does this tell us?
You only need the first and second moments?
In this example, right? And that's because the Gaussian distribution is only characterized by the first two moments. So that's an additional detail of why this is happening. So most importantly, what it's saying is you may not need all of the raw data to come up with your estimation of the unknown parameters, right? So many times we would see this dimensionality reduction, right? So many times, like the data may be large, but to extract the useful information, you may be just, having summaries may be good enough. You may not need all the raw data. And so we'll see this again and again. And especially if you think about complex data such as images, that's huge, right? But not all of that, not each pixel value is important. There's some transformation and some function that is sufficient to tell you what's in the image. And so that's why what we should be thinking about is this notion of sufficient statistic. So what the sufficient statistic is, it's a function of the data. So we'll use this notation T of y. Right, so you take your data and you compute a function. So how do you think I can formally define the sufficient statistic? I mean, the name itself says, right, and we had the example of what it means to be sufficient, but can we formalize that? So when would this function be sufficient?
The way condition on the sufficient statistic is equivalent to condition on the whole data.
Right, so there is the conditioning rule, right? But intuitively what this is saying is it should be as informative about theta as the original data, right? So that's the notion, like you're not losing any information by limiting to sufficient statistic, right? So that's the basic premise. And how can we think about the informativeness? We can do that through the conditioning rule, right? So what the conditioning rule says is, so I'm going to look at the probability of my observed data, right? And then I'll condition it on the sufficient statistic. Is that what you were getting at? So what do you think should be the property of this? Want somebody else to think about this?
It should be equal to the probability of the data from the data, y bar.
So, should it be exactly equal, or should some aspect of it be preserved?
Just some aspect of this normalization.
With what you really want to preserve is this dependence on theta, right? So exactly, so there could be something that's off because of, like that has to do with bi, but not about theta, right? So what, but there is also, it's not exactly that, right? So think about this. What we are putting down is that T of y has all the information about theta that can be extracted from y. So will this conditional distribution have any dependence on theta if it's sufficient statistic? It cannot, right? So that's the definition. The definition is this does not depend on theta. Because you've extracted all the information, so whatever additional randomness that's left, right? So think about, again, the measured theoretic notion I described the previous class for conditional distribution. It's saying like now, I have already told you what is the realization of the sufficient statistic. Now what's the additional randomness in my observed data? That should have nothing to do with theta, right? Because what we've said is all the useful information about theta is already present in T of y. So can you check this rule for the example above on the normal distribution? Right, I guess if you wrote down the conditional distribution, you use the base rule, you write it down, you can check that. But this one sometimes can be strange, right? Because this is the conditional distribution, and I can, if you are kind of not finding it intuitive, I don't blame you. It's not always an intuitive definition. So there's another formulation we'll now use which is more intuitive according to me. At least for me it's more intuitive. So that's another definition, an equivalent formulation for sufficient statistic. But any questions so far? Right, so far what you said is that the definition of sufficient statistic is when you condition on the sufficient statistic, there's no longer any dependence on the unknown parameter theta. Right, so that's, at least the definition is simple. But we'll have another rule to check if something is a sufficient statistic or not, and this is called Neyman-Fisher, I think, factorization. So this is a much simpler rule to check if something is a sufficient statistic or not. And what this says is, if T of y is a sufficient statistic, then when you look at the model, right, when you look at the distribution of your data as a function of theta, you should be able to write down this distribution as a product of two terms. So there is a term that depends only on y and not on theta, right? So there's a term that only has dependence on the data y but not on theta. But then there is a term with dependence on theta, and if something is a sufficient statistic, it should only depend through T of y. Does this definition make sense to you? Right? To me, this is more intuitive because, you're telling me that all the dependence between theta and y is through the sufficient statistic, and so that's this function here. There may be another part, but that has nothing to do with theta. Does this make sense? And this you can almost very quickly check, right? Because if you have you have this parametric distribution, you can quickly check what is the factorization. Can I write down all the dependence on theta through this one term, right? So that's much easier to check, or this one function. So so there is the result, which I guess is this Neyman-Fisher result, that says that the two definitions are equivalent. Meaning you can start with this definition and then it implies this factorization. Or you can start with this factorization and it implies this property on the conditional distribution. So let's see, do we want to try to prove that? So let's try to see how we can do this. So what should we start with? So let's start with assuming the factorization. Right, let's assume that my distribution has this factorization here. Now I want to look at the conditional distribution. Right, so I can naturally use the Bayes rule here. And right? And recall that T of y is a deterministic function of y. Right, so this joint distribution will be the same as the distribution of y only when it's consistent, right? When this T of y, let's say, is equal to u, and then you have the, so we'll write down this, we'll write down the joint distribution. Let me call this realization of sufficient statistic as u, right? In this case, it'll be the same as probability of y, and then I can use this formulation here, right? So, I mean, of course, all this depend on theta, right? So I'm not adding that because it just makes it longer. But do you see this? Right, so how do I write this joint distribution? What is this equal to? Right, so I have the distribution of y, I have this form. And then I'm saying in addition that the sufficient statistic takes this value u. So what is the form of this joint distribution?
It's either f or 0.
Right, so this f, further I can use this factorized form. Right, and in this factorized form, I'll use T of y equals u, right, because that's what I'm kind of setting the value to be u here. Right, so this is if T of y is u, so here I won't do this, right, so that's here, 0 otherwise. And so now how do I compute the marginal probability of T of y? I mean, I have the joint, right? So what should I do about the marginal?
You integrate over the range of.
Right. So let's, for simplicity, say T of y is discrete, just to, it'll work for both, but just for simplicity, let's do this. So if it's discrete, all I have to, let's say y, T of y, both are discrete, right? So just for simplicity. So in this case, I just have to marginalize over y, right? So I can, let's say, sum over y here, right? And then I can sum over y. And so when you're summing over y, you can see all that's just here. Right? Do you see that? And so when I take the ratio, what's left? Right? I have to take the ratio between the marginal and the joint. Do you see that? Right? I mean, this is the same term here. We have the same term both in the numerator and the denominator. Right? So that cancels out, and that's why there's no dependence on theta. So that's how we can prove that if you have this factorization form, you also have this property of the conditional distribution. Is this clear? Any questions? Any questions here?
Sorry, how does the plugging the formula here, the probability of y and ty, are we just plugging the Neyman-Fisher factorization?
Right, so we use this form.
But for the Neyman-Fisher factorization, for the hand side we have f, y, and theta, but here we have y and ty.
Right, so that's a joint, right?
Yes.
But t of y is a deterministic function of y. So if you're thinking about a joint distribution of a random variable and its deterministic function, what is it?
It's still y.
It's still y, assuming that it's consistent, right? Meaning that it's the right mapping of that random variable. And that's why it's this if term, right? So the if is, as long as t of y is u, and that's what you have put in here, right? I mean, the key aspect is when we talk about sufficient statistic, it's a deterministic function. Yeah, and we are using this here. Otherwise, we wouldn't be able to write this. That's a good point. Right? I mean, that's why it's, you can see here, the dependence of theta is preserved. Right? And when you marginalize to get the marginal distribution of the sufficient statistic, it's still the same. And that's why when you take the ratio, the dependence on theta cancels out. Any questions here? Is this clear? Want to make sure everybody is on board.
Can you show how it cancels? Does it take a long time to show how it cancels? I'm looking at it now. I'm trying to see where the
Right.
is at. I get no idea.
So what is probability of t of y? Let's write it down. I'm doing the discrete case just for simplicity. So I have the joint here. What would be the marginal? I would marginalize over the other variable, right? So in this case, we are now marginalizing over the two terms, which means it is, let's say this is equal to u. And then you have marginalization over this. Do you see this?
One more.
Right, you're taking a joint distribution and you're marginalizing on one of the random variables. Do you see that? And that's why when you take the ratio, the dependence of theta is the same, right, in the numerator, in the denominator. Is that clear? Any other questions? T of y and t of y. Because t of y is just, let's say, equal to u, right? That's, let's say, is the condition. And in that case, what you want to ask is, this is just the same as probability of y. Right? Probability of y, because all the randomness is only through y, right? And t of y is a deterministic function of that. Right? And then, so you can write it essentially as, so there is t of probability of y, but then you could have maybe the parameterization through u. And then let's say u is also, in this parameterization, and then it's 0 otherwise. That's why we are doing the two cases. I mean, if the two don't match, then you don't have a valid distribution. Right? This is a property when you take deterministic functions of random variables. Is that clear? Anyone else has further questions? Right? I mean, here we use the fact that this is the factorization of y, and now if I substitute t of y is equal to u, right, only then this is a valid formulation, right? Otherwise it's 0, you cannot use that expression. That's why there's the two cases. Good, so And then we asked, can we think about sufficient statistics that are of lower dimension, so you don't have to take in all the raw data, but only these summarizations, and still be able to get the best possible estimate of theta, right? You don't lose any information using the notion of sufficient statistic. And then we looked at the Neyman-Fisher factorization. That's a convenient way to compute sufficient statistic, right? Because what that says is you can factorize your distribution in terms of one term that has all the dependence on theta and the other that has no dependence on theta, right? And the term with the dependence on theta is only through the sufficient statistic, right? That only has t of y and not anything else about y. And so that's helps you also compute sufficient statistics given a parametric distribution. And the other definition of sufficient statistic is this conditional distribution form, where the requirement is if you condition on the sufficient statistic, right, this distribution of the data should have no dependence on theta, right, because all the information about theta is extracted through the sufficient statistic. And then we saw the exponential form. We'll be using the exponential family in many of the coming lectures. And there, through these canonical parameters, you can look at what are the sufficient statistics, right? So the functions of data which are inner products with the canonical parameters are the sufficient statistics. And then finally, we're looking at hypothesis testing, which will go into depth in the next class, and that involves likelihood ratios, right? Because all you care about is just ratio of likelihoods and not the individual ones, because you're just testing one versus the other. And you can similarly extend that to more hypotheses. Any questions? Great, I'll see you on Tuesday. And the